Hello everyone, I'm Xuan from UCSB. This is a joint work with Robert Balkin from UCSB, Jiequn from Princeton University, Ruimeng from UCSB, and Hector Ceniceros from UCSB. This work is about finding optimal policies for a pandemic using a stochastic game approach and a deep learning algorithm. Here is the outline. First, I will make a brief introduction. Then I will talk about the multi-region SEIR model that we built to model the pandemic. Then I will talk about the enhanced deep fictitious play algorithm that we propose to solve the high-dimensional stochastic game. Finally, I will show some experimental results. Pandemic usually affects a substantial number of people. For instance, in the past 1.5 years, COVID-19 causes millions of deaths. It significantly reduces the economic growth. We do not have many tools to fight with the pandemic. Two of the most powerful tools are the lockdown policies and the vaccination policies. We are going to find the optimal policies for the pandemic using a stochastic game model. Now let's look at the multi-region SEIR model. This is a multi-region model. Suppose we are studying the United States, we will look at multiple states. For each state, the population are divided into 4 groups: susceptible, exposed, infectious, and removed. The dynamics of the 4 groups of population are described in the stochastic differential equations. For the SEIR, they have the superscript n, which represents the state n. The subscript t represents the time. The change of susceptible people, ds depends on the population of susceptible, the population of infectious people in all the states, the lockdown policy L, and the health policy H. VOH represents the proportion of the vaccinated people. The controls here are L and H. Similarly, we have the equations for exposed, infectious, and removed. Each state, the planner of each state seeks to minimize its region's cost within a time period. The cost is defined in equation 1. For each state, the first term represents the state's loss because of the lockdown policies. Second term represents the loss, the cost caused by the deaths of human beings. The third term represents the loss, the cost of the health policies such as vaccination. In this stochastic game, we are trying to find the Nash equilibrium. The Nash equilibrium is defined as follows. For each state, the optimal policy is the one which will minimize the state's cost given the condition that other states are taking their own optimal policies. We are trying to find the combination of all the optimal policies for all the states. To solve the Nash equilibrium, we derive the HJB equations. To get the HJB equations, we generalize the problem. We write SEI as X. Since the SEIR satisfies the conservation laws, the summation of SEIR are fixed. So we only need to solve for SEI and get R by a straightforward computation. We generalize the equations to equation 4. The dynamics could be written in this generalized form. We try to minimize the generalized cost in equation 5. To get the HJB equations, we define the value function of each state by equation 6. Basically, the value function is defined as the infirm cost of each state. The value function satisfies the HJB equations as equation 7 shows. So this is the equation for state small n. We have capital N states in total. So in total, there are n coupled nonlinear equations. For each equation, the dimension is 3n plus 1 because we have SEI and also have time. In total, we have 3n plus 1 dimension. So it's a very high dimensional stochastic game. to solve the high-dimensional nonlinear equation systems, we do not have a nice traditional numerical solver. So we have to use deep learning to solve for the system. In 2020, Han and Hu proposed the deep fictitious play algorithm, which uses deep learning to solve and the idea of fictitious play to solve such systems. We could use deep fictitious play algorithm to solve for our problems. However, since our system is very complicated, if we use deep fictitious play algorithm directly, it will have an issue with the time and the memory. It's very expensive in terms of time complexity and memory complexity. So we propose the enhanced deep fictitious play algorithm, which breaks the bottlenecks of time complexity and the memory complexity. Now I will talk about the enhanced deep fictitious play algorithms. Here is the enhanced deep fictitious play algorithm. In the beginning, here we use alpha to represent the policy L and H. In the beginning, we will initialize the value function V and policy function alpha for all the states. So in total, there are n states, so we will have two n networks. And then, similar to the deep fictitious play algorithm, we will update the value function V and alpha stage by stage. At the beginning of stage n+1, we assume that the value functions for all the states and the optimal policies for all the states at stage m are observable by all the players. So in the stage n+1, for each stage, they know for each state, they know the optimal policies for other states. So they just solve their own optimal policies, given the other states are taking the optimal policies from stage m. So in stage n+1, we use the idea of fictitious play to decouple the HJB equations to n optimization problems. We could solve those n optimization problems in a parallel way. And then we solve for the value function and the policy function for each state, and then we update them. Usually, the solution for the optimization problems are not analytically tractable. We need to solve them numerically. Here, we use the deep BSDE method to solve for the optimization problem. I will explain later. Stage by stage, we will update the value functions and policy functions until the policy function converge to the Nash equilibrium. Compared with the deep fictitious play algorithm, we introduce n additional neural networks to approximate the policies. This makes the algorithm cheaper to evaluate. In the deep fictitious play algorithm, whenever we are going to evaluate the policy function, we need to use the value functions from the previous m stages. So it means we need to store all the value functions from the previous stages. And whenever we need to evaluate alpha tilde at m+1 stage, we need to come back to all the previous m stages. So it's very expensive. In the enhanced deep fictitious play algorithm, we use the neural networks alpha tilde to approximate the policy function. So whenever we need to evaluate the policy function, we just need to evaluate the neural network. We do not need to come back to the previous stages. So it will it will reduce both the time complexity and memory complexity. As I mentioned before, for each stage, we are going to decouple the HJB equations to n separated equations. Here, equation 9 shows the separated value of the separated equations. This is the equation for state n. So we have n such equations. We solve them in a parallel way. For each stage, here is the workflow. We decouple the HJB equations to n separated equations as shown in equation 9. And then for each equation, we find the equivalent BSDE. Then we use neural networks to approximate the value function and the policy function. we solve the corresponding variational problems to get the updated value function and policy functions. Then we go stage by stage until the policy function converges. Here is the BSDE corresponding to the equation 9. So this is a BSDE corresponds to one of the equations. To solve for the BSDE, as I mentioned before, we use neural networks to approximate the policy and also value functions. Here, by straightforward computation, we could replace all the variables in the blue fonts by neural networks. Then we try to minimize the loss. We try to minimize the loss to get the optimal parameters of the neural networks. We would use the stochastic gradient descent method. To implement the algorithm, we need to discretize the BSDE. We use the OLA method to get the numerical discretization of the BSDE. Here is a comparison of the DFP and our proposed EDFP. The memory cost of DFP is OM. The time cost of DFP is OM squared. But for our EDFP, the memory cost is only O1, the time complexity is only OM. Now I will show some experimental results. The first plot shows the numerical. We did the case studies on the optimal policies for the COVID-19. We look at the stochastic game among 3 states: New York, New Jersey, and Pennsylvania. We did the simulation from mid-March to mid-September. At that time, vaccination, it was in 2020. So vaccination was not available. We set V equal to 0. So we just do the simulations to check how the lockdown policies influence the pandemic in different settings. The first plot shows the dependence of policies on hyperparameter A. A represents the planner's view on the death of human beings. If A is large, then the planners pay more attention to the deaths of human beings. They would like to spend more money on lockdown policies to reduce the deaths of human beings. And the experimental results coincide with the intuition. We can see that when A is very large, the planners pay more attention to the deaths. So they would use strict lockdown policy to reduce the number of deaths. If A is small, the lockdown policy is loose. This will lead to smaller economic loss, but it might create more. But the number of deaths might be large. The second plot shows the dependence of policies on theta. Theta is the lockdown policy. It represents residents' willingness to comply with the policy. In the left panel, the theta is small. We can see that the first plot E is the lockdown policy. Plot G is the number of susceptible. Since the residents' willingness to comply with the policy is low, so the pandemic will get out of control. In the right panel, the residents' willingness to comply with the policy is large, theta equal to 0.99. In this case, the number of susceptible people will go stable. It means that the pandemic will be well controlled. From the experimental results, we know that the planners' views on the deaths of human beings and the residents' willingness to comply with the policy are very important. As a summary, we built a multi-region SEIR model for a pandemic to find the optimal policies. We proposed the enhanced deep fictitious play algorithm to solve the high-dimensional problem. Our case studies on COVID-19 shows the importance of planners' view on the deaths of human beings and residents' willingness to comply with the policy. Thank you.